Solutions are homogeneous forms of matter containing at least two components, but they differ from elements and compounds, which we've already studied, in that the proportions of the two components may be varied within rather wide limits. In this film, we're going first to study some factors which influence solubility and which also may influence the rate of solution. Solutions consist usually of a liquid solvent and a dispersed substance called the solute, which may be either a solid, liquid, or a gas. Sometimes we have solid or gaseous solvents also, but these are not of concern to us today. Now, the first important factor which influences solubility of one substance in another is the nature of the solvent and of the solute that we're attempting to dissolve in it. It's an old rule of chemistry that like dissolves like. And while there are some exceptions to this, it will be a good working basis for us today. This means that a polar solvent is useful in dissolving a polar solute, and usually that a nonpolar solvent is a good choice for a nonpolar solute. We're going to illustrate that for you in a few minutes. The rate of solution is often affected by the surface of the solute exposed to the solvent, and we're going to examine that phenomenon. And finally, the extent of solubility and the rate of solubility are oftentimes influenced by the temperature, and this will be illustrated also. We'll first study the effect of changing the solvent while keeping the solute constant. In each of these test tubes, we've placed a small quantity of ordinary sugar, or sucrose. To the tube on the left, I'll add a few milliliters of water. And to the tube on the right, an approximately equal quantity of ethyl alcohol. We'll now stir both tubes for a few moments. After a few moments, we see that the sugar has completely dissolved in the water, while the alcohol has not acted as a good solvent for sugar. Most of the sugar still remains on the bottom of the tube. Sugar, then, is not very soluble in pure alcohol. Is it soluble in a mixture of alcohol and water? We can easily answer this question by adding some water to the tube containing the sugar and the alcohol, and again stirring for a few moments. A few minutes of stirring has been sufficient to cause the sugar to dissolve completely in the mixture of alcohol and water. This solvent system is not as good a solvent for sugar, though, as water is alone. It's useful sometimes to have a solvent in which the solute is not too soluble. Such a solvent is useful for purposes of recrystallization, for instance. And if the correct solubility characteristics cannot be found using one solvent alone, the chemist often employs mixtures of 2 and even 3 solvents to achieve a system which has the properties he desires. Sometimes the procedure of mixing solvents can be carried out in the other direction. In this test tube, we have a small quantity of rosin. This material is soluble in alcohol, but is not soluble in water. I'll add a few milliliters of alcohol to this rosin and stir for a few moments to hasten its solution. After a few moments, the rosin is virtually all dissolved in the alcohol. In this other tube, we have several milliliters of water. Now notice what happens when we pour the alcohol solution of rosin into the tube of water. You notice the milky appearance of the mixture, which is rosin, which has been precipitated out of the alcohol when water mixed with the alcohol. A few moments ago, we saw that where sugar wouldn't dissolve in alcohol, by adding water to the alcohol, we caused the sugar to go into solution. Now here we see the thing in reverse. The rosin did dissolve in the alcohol, but then when we added the alcohol to water, the mixture is not a good solvent for rosin, and the rosin is precipitated. When a solute is not very soluble in a solvent, it's often said to be slightly soluble. But this is a very inaccurate term because even many slightly soluble solutes are much more soluble than others. In this test tube, we've placed a few grams of calcium sulfate, and in this tube, some calcium carbonate. To each tube, we'll add a few milliliters of water. And we'll stir the mixtures. Now, I think it's obvious that neither of these materials is very soluble in water. They are both then slightly soluble. But of the two, which is the more soluble? In order to determine this, we'll wait a few minutes for solution to take place insofar as it will, and then we'll filter both suspensions. After stirring for a few moments, we've permitted the remaining solid in each tube to settle. It's obvious that a considerable excess of undissolved material exists in both tubes. In order to test the solubilities of these two materials, we're now going to filter each solution. The calcium sulfate remains on the left, and the calcium carbonate on the right. After the filtration operation is complete, I'm then going to place a few drops of each solution on a watch glass and evaporate the solution to dryness. Then we'll examine each watch glass to see if there's a residue. On the watch glass on the right, we placed 5 drops of the filtrate from the calcium carbonate suspension and evaporated it to dryness. You can see that there is a very faint residue here. On the watch glass on the left, we placed 5 drops of the filtrate from the calcium sulfate suspension and evaporated to dryness. And here we obtained a very noticeable residue. From this, we conclude that while both calcium sulfate and calcium carbonate are slightly soluble in water, calcium sulfate on the left is still much more soluble than calcium carbonate. From the residue test, which we've just performed, it would appear that the filtrate from the calcium sulfate suspension should contain a significant amount of dissolved calcium sulfate. We can test this suspicion by treating this solution with a few drops of barium chloride, because barium chloride solution reacts with any solution containing a sulfate to give a white precipitate. And the immediate formation of this white precipitate with barium chloride confirms our suspicion that a significant amount of calcium sulfate did go into solution when we stirred the calcium sulfate with water. We wish next to consider the solubility, or lack of it, of 2 liquids in each other. When 2 liquids mix in all proportions, they're said to be miscible. If they do not dissolve in each other, they are then immiscible. In this test tube, I've placed a few cc's of water. And to this, we'll add a few drops of glycerol. Glycerol is a rather heavy, thick liquid. As we add it to the water, the glycerol sinks to the bottom. But by stirring, we find that glycerol and water form a solution and we can say that glycerol is miscible with water. The second test tube also contains water, to which we'll add a quantity of gasoline. Now, in this case, the gasoline floats on the surface of the water, and even stirring will not cause the two liquids to mix. So gasoline and water are immiscible. Now, to this test tube, we can add a quantity of gasoline, and to this gasoline, we can add some carbon tetrachloride. And we find that the carbon tetrachloride and the gasoline form a nice solution, so they are miscible. Now, this phenomena occurs because glycerol and water chemically have much in common. They both contain OH groups. Water and gasoline chemically are very different because water is a polar solvent and gasoline is quite nonpolar. The carbon tetrachloride and gasoline mix nicely because, again, each of these is a nonpolar solvent. We will now consider the phenomena of extraction. This occurs when you have a solute and two immiscible solvents, and when the solute is much more soluble in one of the solvents than it is in the other. In the tube on the left, we have a solution of iodine in water. And iodine is not very soluble in water. It is, however, highly colored, so this solution has a brownish color. But it doesn't really contain very much iodine. Now, I'm going to put portions of this iodine solution in each of these two test tubes. And to the first tube, we'll add some carbon tetrachloride. Now, carbon tetrachloride doesn't mix with water, but iodine is much more soluble in carbon tetrachloride than it is in water. We remove the tube and shake. We find that the iodine is extracted from the water by the carbon tetrachloride and gives the carbon tetrachloride a pink color. Now, to this next test tube, I'm going to add some potassium iodide solution. Now, potassium iodide reacts with the dissolved iodine in the water. The I- ion from the potassium iodide reacts with the I2 molecule to give an I3 ion. And this ion, being charged, is presumably not very soluble in carbon tetrachloride. And in fact, when we add carbon tetrachloride to this solution and shake as before, we find that the pink color in the carbon tetrachloride layer is noticeable by its absence. From this tube, then, the carbon tet was able to extract the iodine because the iodine was much more soluble in the carbon tetrachloride than it was in the water. But over here, when we've converted the I2 molecule to the I3 ion, this ion was more soluble in the water, and the carbon tetrachloride was not able to extract it. One of the more obvious factors which influences the rate at which a solute dissolves in the solvent is the state of subdivision of the solute. I think obviously solution takes place only at the surface of the solute crystals, and the smaller these crystals are, the more of the solute is at the surface of the crystal, and therefore more of it is in contact with the solvent. In these two tubes, we've placed, in each case, crystals of copper sulfate. This tube contains rather large crystals, while in this tube, the crystals have been pulverized and reduced to the form of a very fine powder. Now, to each tube, we're going to add 15 milliliters of water. And then we'll shake both tubes vigorously for a few seconds. and then we'll replace both tubes in the clamps. After a few minutes, you can see that considerable quantities of crystals still remain in the tube where we started off with large crystals in the first place. While in this tube, where we started with powdered copper sulfate, all of the crystals have disappeared. This confirms our suspicion that increasing the surface area of the solute will increase the rate at which it dissolves. In this experiment, we're going to study the influence of temperature on the solubility of a solid solute. In the test tube, we placed a few milliliters of lead acetate solution. And to this tube, I'm going to add 4 drops of dilute hydrochloric acid. Now, in a few seconds, we'll see the appearance of a white crystalline precipitate, lead chloride. I think you can see this precipitate forming in the tube now. Lead chloride is only moderately soluble in cold water, and a reasonable quantity of this material will precipitate from the solution in the course of a few seconds. Now we're going to warm the solution with the burner. We'll continue to stir to avoid bumping in the solution. I think you can see that the lead chloride is rapidly going into solution at the higher temperature. It remains to be seen if we can cause it to reprecipitate by lowering the temperature. In this beaker, we have some ice water. We'll lower our tube of lead chloride solution into the ice water and once again stir. I think perhaps already you can see the formation of some small crystals of lead chloride in the test tube. They're now present in some quantity. It's obvious then that the solubility of lead chloride changes quite drastically with the temperature. Lead chloride is a salt which is very much more soluble in hot water than in cold. There are many such salts, and in fact it's a rather general property of solid solutes that they are more soluble in warm solvent than they are in cold, although this is not an absolutely general rule, since there are a few exceptions. In this case, however, lead chloride is behaving normally, showing much higher solubility in the warm water than it does in the cold. We've just seen that some solutes are much more soluble in hot solvents than they are in cold solvents. That is, their solubility increases as the temperature rises. This brings us to a consideration of an interesting phenomenon called supersaturation. In this flask, we've placed quite a large amount of the salt sodium acetate and a relatively small amount of water. Now, sodium acetate is much more soluble in hot water than in cold. So we heated this flask, and all of the sodium acetate dissolved at the higher temperature. Then we very carefully cooled the solution down. Now, here we have a situation where there is much more sodium acetate dissolved in this water than can be in equilibrium with solid sodium acetate. The solution is supersaturated. However, there is no solid sodium acetate present, so equilibrium is not established between the solid and the dissolved solute. On the tip of this spatula, I've placed a very small crystal of sodium acetate. But that small crystal will be enough so that when added to this flask, it brings two phases into presence in the flask, the dissolved sodium acetate and the solid sodium acetate. And when that happens, equilibrium must be established, and a great amount of sodium acetate will be crystallized from the solution. I'll now add the small crystal to the solution in the flask. So much of the sodium acetate crystallized from the solution that there's scarcely any liquid phase left, as we can illustrate by tipping the flask over. You can see a very small quantity of liquid leaking out of the crystals here. The rest of this large mass of material is solid sodium acetate, which was present in the original solution in a supersaturated condition. We'll now proceed to examine the temperature effect which is produced when a very soluble solid dissolves in the liquid. In this test tube, we've placed 10 milliliters of water. We've inserted in a thermometer in this water, and we'll measure its temperature before the solute is added. The temperature of the water before we add the ammonium nitrate solute is 38 degrees. We're going to use ammonium nitrate as the solute in this experiment because of its high solubility in water. I've placed some crystals of ammonium nitrate on this spatula. I'll remove the thermometer from the test tube and add the ammonium nitrate to the liquid. Then we'll replace the thermometer in the tube and stir. The temperature is falling quite rapidly. It's now down to 20. Mercury is now approaching the 10-degree mark. And seems to be stopping at about this point. Therefore, the temperature of this solution has been lowered from 39 to 10 degrees by the heat absorbed by the ammonium nitrate as it went into solution. We will now examine the effect of the presence of a non-volatile solute on the vapor pressure and therefore on the boiling point of the solvent. In this test tube, we've placed some water, a few boiling stones in the bottom. We're heating with the Bunsen burner. We've placed a thermometer in the tube with its bulb dipping into the water, and the thermometer now reads exactly 100 degrees centigrade, the boiling point of water. Now, to this tube, we're going to add quite a large quantity of urea. As we add the urea, the boiling point of the solution should be raised because the presence of the non-volatile urea will lower the vapor pressure of the water. I'll now add the urea, which we have on this paper. Of course, the liquid stops boiling now because the cold urea has lowered the temperature of the mixture. And we'll replace the thermometer. We'll now continue to heat with the burner and see at what temperature the solution now boils. We're now heating the solution with the burner. The temperature of the solution was lowered by the cold urea, but it's now rising. And as you can see, the solution is now boiling at about 104, 105, 106 degrees centigrade. The presence of the non-volatile urea has increased the boiling point of the water from its normal 100-degree temperature to about 107 degrees centigrade. In this film, we've examined several of the factors which influence solubility and the rate of solution. With respect to point 1, the nature of the solvent and solute, we examined first the solution of sugar in water, but found that sugar was insoluble in alcohol. Next, we saw that rosin is soluble in alcohol, but insoluble in water. Thirdly, we saw that a solution of iodine in water is such that when carbon tetrachloride is added, the iodine, being much more soluble in the carbon tetrachloride, is extracted by it and passes into the carbon tetrachloride layer. We examined two rather insoluble solutes, calcium sulfate and calcium carbonate, and found that although they are each only slightly soluble, it's possible to differentiate between them, because calcium sulfate is more soluble than calcium carbonate. With respect to liquid-liquid mixtures, we found that water and glycerin dissolve in each other very nicely, that water and gasoline do not, but that gasoline and carbon tetrachloride dissolve nicely in each other. Coming to point 2, we saw that finely divided copper sulfate dissolves in water very much more rapidly than large lumps of copper sulfate. Under point 3, we made some lead chloride. We found that it was very much more soluble in hot water than in cold water, and we found this solution, when cooled, caused the lead chloride to reprecipitate. And finally, we found that the presence of a non-volatile solute lowered the vapor pressure of its solvent and thereby caused the boiling point of that solvent to increase.